Um, the alternative approach, which is not to use the characteristic functions but work directly through transforming the densities or the cumulative distribution functions, is, well, will always give you the same answer, but for developing exact distributions is my preferred way of approaching it, except in a few cases. On the other hand, the proofs of the approximations can often be made this way, in a much more direct fashion. In order to prove approximations using characteristic functions, you first of all have to prove approximation theorems for the characteristic functions themselves, and then you have to integrate the characteristic functions back again to get the cumulative distribution functions, and show that you can still carry through the approximations at the stage at which you integrate again. So you find yourself with a structure of proof which in effect requires two separate theorems, one that the characteristic functions are going to be good approximations, and then that you can integrate them again. On the whole, I think it's a matter of horses for courses, that for some cases it's much easier to work using the characteristic functions. For others it's easier to go through the direct route. The use of characteristic functions often has the problem that it involves, complex variable theory of a fairly complicated kind. That doesn't make it a great deal more difficult, except it's a kind of different specialization. And so it may be for some people much easier to work by the direct route. To some extent you can avoid this problem of complex variable theory by using the idea of conjugate functions, and I will talk about that later. Well, we're about ready, are we?
Yes.
Okay. The topic of this lecture is the use of characteristic functions, and in particular the use of the method of integrating the characteristic function numerically to provide close approximations to the distribution functions of certain kinds of statistics used in econometrics. I think it's perhaps worthwhile to specialize on the work that is being done on Durbin-Watson statistics and related test criteria, because these provide both a good example of the technique and at the same time it's easy to generalize this technique to any case where the characteristic function is available in analytic form. So in fact what I'll first do is to go through the algebra of the straightforward Durbin-Watson statistic again, and then look at the way that one can derive the corresponding finite sample distributions. Using a more or less standard notation, let's assume we have the regression coefficient of the normal type with k regressors making a k by t matrix. Beta then is the unknown coefficients to be estimated, a k times by one vector. U is a normally distributed vector, and though we don't have to do this, let's start out by the making the usual assumption that we have serially uncorrelated, identically distributed errors. And then we start out by estimating beta as beta hat, the OLS estimator, and as usual, if we put y from the first equation in here, we will find that this is just and I'm going to write that. Then defining u hat in the usual way, one substitutes to get that it can be written either in the form I x prime minus 1 x prime y, or alternatively, again substituting from the first equation in there, the same thing. Well, we can write this in the form equals QU, where Q is defined as the idempotent matrix in the square brackets. And that, of course, is a T minus K order symmetric idempotent matrix. It's convenient to introduce the notation D for the difference operator, and this is simply a matrix T minus 1 by T, which has its first row minus 1, 1, then T minus 2 zeros, and then simply moves up one place as one goes from row to row, finishing with a block of T minus 2 zeros and minus 1, 1. The effect of that, of course, is simply that if you apply it to a vector x, it yields you the vector whose elements are xt minus 1. It's just the difference operator.
That second row, can't remember from that Watson, but minus 1,
So, of course, I'm sorry. Yes, I'm just putting down an extra minus when I don't need it. Now, clearly, if we look at the Durbin-Watson statistic, which I'll define as capital R one has that is going to be given by u hat d, d u hat over u hat and u hat. It's sometimes regarded as necessary to put in a deviation from the mean here. Instead of u hat itself, take u hat minus u bar, for example. But I'm assuming that we've got a constant term among our x's, so that the mean is 0 anyway. Yes. It's usual to take in the Durbin-Watson notation the d prime d matrix to be the matrix A, and of course I think you're all familiar with the elements of the matrix A, the T minus 1 rank non-negative definite matrix. Clearly also we have that this is U Q D prime D Q U U prime U. Sorry, U prime Q U. Now, what we need to do in order to go on to the next stage is to factorize Q itself. It's a familiar fact that Q can be factorized into, well, I'm simply going to call it HH prime. H is T by T minus N and satisfies the equation H prime H is the unit matrix of order T minus N. This follows, of course, from the usual properties of symmetric idempotent matrices. Then if we substitute that into our previous formula, of course we get that R is U prime H prime D prime D H prime U, similarly down here. And if we now introduce U star H prime U, we can write this in the form U star primed and then H prime D prime D. Sorry, as usual I'm a bit too rough and ready with my primes, so I need to have D prime D in the center here. H U star upon U star and U star. And using the usual properties of orthogonal transformations, this is essentially an orthogonal transformation of the U's into the U stars, we notice that we also have that U star is normally distributed, mean 0, variance sigma squared I, but this is now I of order T minus N. Well, this type of formula is the formula that the Imhoff procedure is particularly appropriate to deal with. What we have here is a ratio of two quadratic forms, one of which happens to be transformable to just a sum of squares in the denominator, but in the numerator we have a general, in this case, non-negative definite matrix, order T minus N by T minus N. But the Imhoff procedure will deal with any case where we have a ratio in which the denominator is a non-negative definite matrix. and the numerator doesn't have to be definite either way, positive or negative. Any quadratic form can be in the numerator. But let's proceed at the moment to consider this particular case, and I'll introduce the notation W for the quadratic form in the numerator, or rather the matrix of the quadratic form in the numerator. And the obvious transformation to make at this stage, which reduces the number of parameters we have to look at, is to the usual eigen value form, the usual canonical form. And so let us introduce a second orthogonal transformation to get W into its canonical form, into its diagonal form. And suppose that we can write W is given by L lambda L prime, where L is a square orthogonal matrix, lambda is the diagonal matrix with roots lambda up to lambda t minus n, zeros everywhere else, and introduce u dagger equals L primed u star and so write this in the form u dagger primed lambda u dagger over u dagger primed u dagger. Now, this makes it clear, since we have again that all we're doing is to take an orthogonal transformation of our u star now, and so that again we shall have normally distributed variables with identical independent distribution, that the distribution of the ratio only depends upon the latent roots lambda. Well, that's a considerable simplification, because it means that we can write a routine for calculating, first of all, the latent roots, a computer routine, and then a routine for calculating the CDF, which depends only upon the latent roots as transmitted to it. And the same kind of thing applies in a much wider context. For example, just to quote a couple of recent works that are considering this same kind of problem, but in a context in which the U's are no longer serially uncorrelated. There's a couple of articles by myself and Alok Bhargava in the Econometric in 1983 discussing Durbin-Watson statistics for cases where the U's are random walks, where the same kind of algebra applies. So just to generalize what the criterion is that we're looking at, let's now generalize to a case where we have R is U primed AU, U prime BU, And B is non-negative definite. B is non-neg def. You could use this kind of generalization if you assumed a general covariance matrix for the U's in the initial formulation. You could easily find that you got the same kind of formulae, except that you have different quadratic forms in the numerator and denominator. So I'm just looking at the very general case. The only point of making this restriction is that we want to ensure that u primed, b u primed is greater than or equal to 0 for u.
So you assume that the 0 happens with very low probability like this?
Yes. That is certainly true, that as you say, it doesn't very much matter that we're allowing the thing to be 0, because if the u's have got a continuous distribution, they certainly have if they're normally distributed, then the probability that u prime bu equals 0 is obviously equal to 0. So it doesn't affect the distribution. What we're then going to look at is the probability that r is less than or equal to r. And of course, if r is less than or equal to r, that implies that u into a minus rb u prime is less than or equal to 0. And so we approach the matter by saying, okay, we've got a given value of r, we simply take the matrix A minus RB and we look for the probability that C, which is defined as A minus RB, probability R less than or equal to R is equal to the probability that U prime C U less than or equal to 0. Well, again, I see, I'm sorry, that I've slipped in a surplus prime on my second U in the previous equation. The big simplification is that now all we're looking at is a quadratic form in the U's rather than looking at the ratio of quadratic forms. And again, we can simplify our expression by transforming to a canonical form. As before, though it's a slight change in the use of the symbols L, lambda and L prime, but as before, let's take it that the canonical form can be written as here, with L an orthogonal matrix and lambda a diagonal matrix with diagonal elements lambda I. And so then, more or less as before, define U dagger is L times U, or rather L prime times U. And you see that your probability that R less than or equal to R is the same as the probability that U dagger find lambda U dagger less than or equal to 0, where lambda, capital lambda, is the diagonal matrix with elements lambda 1, lambda 2, up to lambda, well, lambda 1, lambda 2, lambda 3, and I won't specify what the dimension of lambda is, though of course it's the same dimensions as the dimensions of the vector u. Previously it was t minus n, now I haven't bothered to say what it is. Simply I haven't defined the dimensions of the u matrix, of the u vector. Of course, in general, if we were to say, okay, this is the original u that corresponds to a sample size t, we could do this simply by having some 0 roots mixed up in here, and that would effectively reduce the dimension of the u vector, and so we might as well take out all the 0 roots that arise in this definition. And only consider the non-zero roots. In general, if R, A and B are non-negative definite, if R is positive, then in general you will find that you have positive and negative roots. If you make no restrictions about A and B, about A being non-negative definite and allow it to be simply symmetric, then again you can have positive or negative roots. Now, there is an obvious result which we don't need to spend any time on, and that is that if all the latent roots lambda are positive, then this lambda is a positive definite matrix, and therefore this is always positive, and so the probability is 0 of R being less than R. So in fact, we're really only interested in cases where the roots lambda are both positive and negative. If all the roots are positive, then, as I say, the probability is 0. If all the roots are negative, then the probability is 1. Well, now, one further complication which it's easy to take account of in this context, which, in fact, I will now introduce, is the possibility that U dagger, we have now postulated that the distribution is as stated here with a 0 mean. But in fact, for some problems, it's of some interest to make the additional assumption that the mean is non-zero. And in fact, the other thing that we can do immediately to simplify this problem is to note that sigma squared is not important here. The reason is that if you change sigma squared, you simply scale up and down the quadratic form, but you don't change the probability that it's going to be less than or equal to 0, since we're particularly looking at the value 0 here. So, and clearly, going back to the original Durbin-Watson distribution, the case there is similar because you're looking at a ratio of two quadratic forms which is zero homogeneous in the u's, and therefore any change in the scale of the u's doesn't affect the criterion. So it's convenient to make two changes here. First of all, to put sigma squared equals 1, and then to assume a non-zero mean. To give you one example of a case where such a non-zero mean would be useful, one might be interested in what happens to the Durbin-Watson statistic if you misspecify the form of the equation. If you estimate the equation that I originally stated, but in fact the true equation is of the form if you work out the properties of the Durbin-Watson statistic in that case, you'll find that you have exactly the same formulation. The only thing that's going to happen is that your u's, instead of being normally your u hats, instead of being normally distributed with a zero mean, are normally distributed with a non-zero mean, and then that carries over to the transformed u daggers. And in fact, there are quite a large number of test criterion of various kinds where it's convenient to make this kind of assumption. Well, let me at this stage specify that I'm going to actually assume that the dimension of u dagger is capital K, just to be able to write out my formula explicitly. Okay, well, this is the kind of thing that we're interested in dealing with. Now let me say something about the use of characteristic functions in a general kind of way. This will not be much of a general exposition, but I put it in simply for people who are not very familiar with characteristic functions. I'm actually going to start with the moment generating function, and then discuss characteristic functions immediately afterwards. My moment generating function I shall call pi of s, which is the expectation of e to the s. Well, I'm going to use y. I'm sorry. I have used y. Unfortunately, there's a bit of a clash here of notation. This has nothing to do with my previous y. This is simply any stochastic scalar stochastic variable, any scalar sample function. S can be real or complex. Very often, if one's not too familiar with complex variable theory, one may start out by looking at e to the sy, d, f, y, f being the cumulative distribution function of the y, or if you have an absolutely continuous variable, then one uses the density little f y dy. The reason it's very often necessary to look at y imaginary is that for y imaginary we know that this integral is well defined. Assuming that f of y is a continuous function of y for all values of y, then clearly the only convergence problem is on the tails. However, frequently we will have to consider cases where f of y, e to the sy, does not exist in order that a minimal condition, for example, that the integral should converge as y goes to infinity, is that e to the sy fy is bounded. Of course, in fact, that it should tend to 0, and we can't rely upon that for large positive values of s. And similarly, on the negative tail, this will not converge in some cases for sufficiently large negative values of s. On the other hand, if f of y behaves exponentially upon its tails, then there may be a finite range of real values of s for which this phi s is defined, and this plays an important part later in the discussion of conjugate distributions, as we shall see much later in the course. But at the moment, let's note that it's often enough to only look at the case where s is imaginary, and so I'm going to introduce a second notation, which is psi t is equal to phi I t. However, let's also have a discussion as to why it's relatively easy in some cases to get an analytic form for the characteristic function. Very often we have some set of variables p with known distribution, so a vector of variables p with a known distribution. For example, these might be the data second moments or something of this sort. And we're going to define our y as a function of p. In fact, I'm looking at the scalar case at the moment, so g is just a simple scalar function of p. Well, of course, if we're going to define phi of s, we're going to simply take it as the expectation of x s g p. This may not be too complicated a function of p, and if p has a simple, for example, a normal distribution, or some relatively simple distribution, then we can make this integration relatively easily. Much more difficult, on the other hand, to transform the distribution functions directly. So it's very often the case that we can work out the characteristic function for g of p in a simple analytic form where we can't work out the actual distribution function for g of p directly. We shall have an immediate example of this when I come to look at our particular kind of generalized Durbin-Watson statistic problem. Let's also note some elementary properties of phi of s. First of all, clearly phi of s is real if s is real. Secondly, phi of 0 is 1, simply by noticing that we're then taking the expectation of 1. Next, if s equals it, then we note that phi it is, phi minus it is simply the complex conjugate, pi star. I'll use star as a conjugate. Or perhaps, no, I better put the star up. So star simply means complex conjugate. That's easy to see when you simply substitute in there. Notice that changing the sign is simply going to change the sign of the imaginary part of the integral. And that phi it always exists simply by taking absolute values throughout. One sees that the integral defining phi it is absolutely convergent. And in fact that the absolute value is always less than 1. Perhaps I write that one down, phi it is less than the integral using the usual property of that the absolute value of an integral is less than the integral of the absolute values of the integrand, and of course this is just 1, and dfy integrated from minus infinity to infinity is then equal to 1. So, it may very often be the case that we can define phi of it, and then we want to recover the cumulative distribution function, and we can make use of the general inversion theorem for Fourier integrals. And I shall simply quote the usual formula for this. This is given in all the usual textbooks in one form or another. I'll first of all quote one in terms of S's, where the basic idea is that one is now considering integrating up the imaginary axis from minus I infinity to plus I infinity. And one has to take this integral in this form, or alternatively, I suppose the more useful form is to substitute s equals it and then integrate t from minus infinity to plus infinity, and that's the same thing. So minus RT1. Still IT, psi t dt. This is because that when we replace ds by I dt, we get a kind of another I, which ensures that we don't cancel out our previous I. Yes. Well, you see how the i's work out fairly easily once you put ds equals I dt and s equals it in there. Now that's okay, but of course what we really want to do is to say what fy is for some particular value of y. This formula holds true where the y1 is greater than y2, but one might as well, in fact, allow, specify that y1 is greater than y2, just to be a little more definite about the formula. Now that's the formula that's usually given in the standard statistics texts, but what of course one wants to do is to know what the formula is for y1 without having y2. In order to sort that one out, what one has to do is to consider what happens as y1 tends to infinity. You see that there's a bit of a problem here. Since your path is going through the origin, you have that there's a factor 1 upon t here, which looks as though it's going to make the integrand have an infinite value, but that doesn't happen because at the same time the numerator becomes 0, and so one simply takes the limit as t tends to 0 here. You might expect that as t goes to, as you consider what happens here as y1 goes to infinity. Let's see. Now the obvious thing to do here is to make fy2 tend to 0 by considering the limit as y2 becomes large and negative, tends to minus infinity. But in order to avoid this question of what happens at the origin when you do this, what it's normal to do is to consider a revised path which avoids the origin by taking a slight loop round it. As is well known, such modifications of the path of complex integrals don't affect the value of the integral, so one takes a small semicircle of radius delta round the origin. What one can show, but I'm in fact going to skip round this point, is that if you allow y2 to tend to minus infinity, yes. No, I see. I'm misstating my notes. What I'm going to do is to allow y1 to tend to plus infinity and keep y2 unchanged. So the first term here is going to tend to 1. That is, the fy1 is going to tend to 1. y1 tending to plus infinity. And it's simple at the same time to replace y2 simply with y, so that our right-hand side becomes 1 minus fy, and of course the second term here is unchanged. And the the first term here is unchanged because we're not changing the value of y2, we're simply holding that at the value y. And what one can demonstrate is that the second term tends to 0. So one finds oneself with a formula 1 upon 2 pi I infinity minus I infinity exp minus sy over is pi s ds. And it's at this point that it becomes clear that this little ditto around the origin is necessary, because otherwise we have got that the integrand is of order 1 upon s at the origin. Now, the effect of this is now rather complicated. What we can do is to write this now in terms of t, and at the same time consider separately the effect of the integral from minus infinity, in terms of t, of course. What we're now doing is to take minus infinity. If we look at s here, we're going up to s equals it. We're going under the origin in a positive direction, and then we're going, and in effect we're going from in a backwards direction around the origin, and at the same time we're then picking up at delta going to plus infinity. We split our integration up into these 3 parts. We look at the integrand that we have for the around the origin, and we find in fact that at the origin exponential sy and phi s are both equal to 1, and so in effect we're just integrating 1 upon is as we take this small semicircle. We find the effect of that is simply to give us a half, and then we have 1 upon 2 pi I, taking the I that we have here outside, and a double integral infinity delta plus minus infinity to minus delta times by exp ity psi t dt upon t. At this stage, of course, what we need to do, if we're not going to use complex algebra in the computer, is to separate out real and imaginary parts of psi t and then consider what this product term gives us. In fact, if we write psi t is psi 1t plus I psi 2t, it's not too difficult to derive the following formula. I'm skipping rather at this stage because I don't think we're any of us too interested in these details. We can let delta tend to 0, it turns out, when we look at the form of these formulae. Over t dt. Well, I've made rather a hash, I think, of presenting that formula very clearly for anybody, including the recording, so let me represent it in a slightly different form. You see that we've got 1 minus fy equals this, and the conclusion we draw is that fy itself, that is the cumulative distribution function, is given by a half minus 1 upon pi infinity naught psi 2 cos ty minus psi 1 sine ty, that's a cos ty minus psi 1 sine ty upon t dt. Well, that's a fairly rushed discussion of the way that this actual formulae, which is the one actually uses, comes from the kind of general formulae given in statistics textbooks, where you have two y's. To avoid this kind of problem of how you treat the origin. Now all you have to do then is to substitute in the functions psi 2, psi 1 into some numerical integration routine to actually compute the cumulative distribution function. And the Imhoff program, which is very generally used to compute simple the cumulative distribution functions of simple econometric estimators, uses the standard Simpson rule type of procedure. But clearly, one of the problems that we need to think about is that this is an infinite integral also, so that there are two things required for a Simpson rule procedure. One is to truncate this infinite range of distribution of integration by taking a sufficiently large value, say capital K. K will very often be taken in the Simpson rule procedure as well. The problem is that it is the choice of K is model dependent or function dependent, K may range from anywhere from 10 to 100 in the Imhoff procedure, depending upon how difficult it is to get this integral to converge. The other thing that we have to do with the Simpson rule is, in fact, to approximate by taking a series of short intervals and approximating the integral over each short interval in the Simpson kind of way. And so there's a choice of the short interval. For that little h, well, that may involve you splitting up the range of integration into anything between 100 and 1,000 or more than that short intervals in effect, and taking a sum of the values of this integrand appropriately weighted for rather a large number of values of t. So it takes some time to do this. It also takes some time if rather than having a particular value of y, one is interested in finding the value of y that corresponds to a particular value of f, as you often are in setting up a confidence interval. And so what one then has to do is to use some kind of inverse integration procedure, inverse interpolation procedure, to find the appropriate value of y for a given f. Though I've talked about this particularly in connection with Imhoff, perhaps I should mention, by the way, that the whole package for computing the lambdas and the psi's 2 and psi 1 that correspond to the a general quadratic form, a general set of lambda I and mi, is discussed at some length in the book by Abrahamse and Kurtz. That has always the property that it is 0 at t equals 0. Psi 1 is not, but of course that's multiplied by sine t1. Yes, okay. So, I was just referring to the Abrahamse and Kurtz book, which is given in the general list of references. This has got a Fortran program for doing the whole thing, which works very well and which I think is universally used nowadays. So it's not particularly for the theory that I refer to Abrahamse and Kurtz, though they in fact discuss the theory very well. Well, now let us return to the special case where we're looking at the distribution function of quadratic form. Notice the specialization that though the Imhoff program will deal with is less than r, less than or equal to r. In fact, we normally want to use the case where it's actually equal to r. In other words, we're looking at the f0 here. We're looking at the case where we want the cumulative distribution function for the particular value of y, which is 0. In other words, if we're only looking at the value of y equals 0, we can specialize this formula even more. Now, all I have to do in order to kind of finish this, round this off perhaps, is to look at what the form of the characteristic function is for this particular y. In effect, what I'm doing is to say, okay, y is u prime lambda u, and u is normal with m as mean and I as the variance matrix. So we have two k parameters, the lambda I equals 1 to capital K, and the mi, and what one needs then is a program that will, for this particular y, compute the characteristic function. Well, let's look at that very briefly. In this case, it turns out that we can look at phi. In other words, we don't have to go into the complex domain in order to find what our phi is. It's exponential u prime lambda u is our phi. Sorry. There's an S here. Phi s is defined as the expectation of the exponential, and so we find ourselves doing a multiple integration and then we write down the corresponding density well, what we notice is that we have terms of the same kind in the density as we have in the exponential, that we're taking the expectation of. And so we have to combine together the two exponentials, and perhaps it's simplest to look at what we've got in the combined exponential. So let me now write down integrand equals exponential. Sigma lambda k uk squared times s minus a half uk minus mk all squared. You see, the great advantage of transforming to canonical form is that now we've got it broken up into independent terms. Each of these exponentials is independent of each other, and so we can integrate each separately. And so let's have a look at what happens if we just take one of these terms and integrate it, exp lambda k s uk squared minus a half uk minus mk squared is equal to exp minus a half, because what I'm going to do is to use the fact that this is similar to a single variable normal integral, normal distribution integral. And let's see, close that bracket, close the second bracket, and then duk. So that's the integral that we're going to be considering. Of course, we could take a 1 upon the square root of 2 pi on the outside, 1 upon the square root of 2 pi on the outside, and the integral goes from infinity to minus infinity. Well, perhaps I won't put in the full detail of the way that one does this transformation. I'll just say what's required to be done. What one does is to take a transformation z equals uk minus mk upon 1 minus 2 lambda k times s, and multiply that by the square root of 1 minus 2 lambda k s. Now, this, to say where the integral, this term comes from the fact that one wants to make this exponential minus a half z squared plus something else. So my strategy is to say, okay, let's introduce a z variable such that you can write this in the form, if you like, x minus half z squared plus a, and it turns out that in order to do that and get the uk squared term and the uk term correct, I have to make this transformation. Now, so the effect is that we have here 1 upon square root of 2 pi, infinity minus infinity, x minus a half z squared, then the additional a that we have to use here turns out to be exp lambda s mk squared over 1 minus lambda, I'm sorry, that should be lambda k s mk squared, 1 minus lambda k, 1 minus 2 lambda k s. Then, of course, in place of duk, we want dz, and duk equals dz upon 1 minus 2 lambda k s square root of. So here we're going to have dz square root of 1 minus 2 lambda k s. Okay, so, sorry, this integral becomes this integral after we change the variable in this way. So finally, now the exponential minus a half z squared cancels out the 1 upon square root of 2 pi, because of course this whole integral dz, sorry, take the dz over from here to here, this whole integral is just 1, and so we see that we can write for psi phi of s that phi of s is actually equal to the product over k, or factors k, of, first of all, 1 upon square root 1 minus 2 lambda k s, and then x s into lambda k into mk squared into 1 minus 2 lambda k times s. Okay, so there's the explicit expression for phi of s. You notice that s, this is well defined so long as the 1 minus 2 lambda k s is positive for all values of k. So that gives you an upper limit on how large s can be. But in any case, we're only interested in working this thing out for s imaginary rather than s real. And so what we have to do is to substitute for sit, then separate out the real and imaginary parts of the resulting function. If we're only interested in the problem that we started with, that is looking at the probability that the quadratic form is less than or equal to 0, then in fact all we need to do is to sort out the imaginary part of this. Now, I'm not going to go into that degree of detail. If you don't like the kind of algebra involved, you can get a computer to do it for you, in fact. The computer will, or at least some computers, have real and imaginary algebra, so that you could simply plug this formula, write a routine which would compute this formula for the case that s is imaginary. But in any case, one sees how one proceeds from here is simply to take the imaginary part of this for s equals it and plug that into the Simpson integration side of the program to compute the distribution function. Just using the formulae, well, to remind you, just using the formulae that f naught equals a half minus 1 upon 2 pi integral psi to t upon t dt. Well, that is all provided for very well by the Hamza-Kurtz program. I think this does give you an example of how one can use characteristic function approaches to getting these finite sample distributions. And in fact, the Imhoff program itself is very frequently used to compute exact distributions in comparison with various approximations to these cumulative distribution functions. And perhaps that is the chief interest of it, apart from the use of it for the kind of statistics that I've discussed at the beginning of the lecture.